Okay, great. So let's get started. So it's our pleasure this week to have Carri Chen joining the SNAPP seminar. So Carri is the John Howard Professor of Business in the DR division at Columbia Business School. She's the winner of several awards, including the M. Young Scholar Prize. Her work applies tools from applied probability to solve problems in operations, particularly in healthcare applications. And we're going to hear about one such story today about modeling sunk costs using queuing theory. So, Carri, please take it away.
Thank you so much, Siv, and thank you to all the organizers for having me, and thank you to all of you for being here. So I'm going to tell you a little bit about some work that I've been doing with our former PhD student, Jimmy Chin, who's now a faculty at UT Dallas, and my colleague, Jing Dong here at Columbia Business School. This is for a general service setting, but it was motivated by a healthcare problem that we had been working on previously. And so my hope is to give you a little bit of the background of the phenomena that we've observed, and then how we decided to model it and get some insight into managing such a system. So just to set the stage for motivation, certainly we've all experienced it. I'm giving a seminar over Zoom. So, it is certainly the case that service systems are moving towards more online environments, but also with this synchronous option. So it's not just going online and doing something and then waiting for a response, but actually having live interactions with a service provider. Many of you know that I work extensively in the healthcare space. So this was primarily initially motivated by work in the telehealth space, which has grown substantially, certainly with COVID. But you also see this in online banking and online tutoring. In fact, which I guess as academics maybe can be concerning or actually wonderful, in the sense that it is opening up more access to education and knowledge. So it's actually pretty remarkable. I found some statistics on the online tutoring space, and it is just exploding quite rapidly. And so a lot of it is being driven by what's growing in the US. We live in a very achievement-oriented culture. And so I think there's a lot of pressure amongst parents, amongst students, to really engage and get a leg up by connecting with educators and tutors that could be anywhere in the world. In an area that I'm more closely connected with in the telehealth space, prior to COVID, yes, there exists some telehealth use, but it was quite limited. And it is skyrocketed. So this is the online doctor consultations by revenue across the entire world. And so it exploded during COVID, and it's expected to kind of like plateau, in part because, of course, within the healthcare space, there's core parts of the service that need to happen in person. But there's this sentiment that online telehealth type of services are going to be a core part of the service package that is available to patients going forward, especially for those with chronic diseases that maybe need to visit quite regularly. So in all of these service settings, a core challenge that often arises is service incompletions. So service incompletion can happen in a number of ways. People may not show up for service at all, or they may show up and then abandon or balk once they see what's going on in the system. So we're going to be thinking about this phenomena where a customer arrives to the system, but then decides to actually abandon and leave without receiving the service at all. And this is problematic. We, as people in the applied probability space, spend a lot of time trying to understand this type of behavior, but it ultimately, for the service providers, is quite problematic. So From a revenue standpoint, whether it's in healthcare or in retail, banking, tutoring, there's a loss of revenue for that service not happening at all. The customers may get frustrated, their satisfaction and their retention may actually decrease because they're not getting the service quality that they expect. And then certainly in the healthcare space, if these are appointments that do need to happen, there's care does need to be provided to the patient, there's an increased risk of adverse quality events. So this whole work, and I promise I will get to the model at some point, but we started looking, Jimmy's dissertation work was looking at telehealth appointments in an outpatient setting. So think of this as primary care. You get your annual visits, going for sick appointments as well. And we are looking at the contrast in behavior between in-person appointments and telemedicine appointments. And a priori, we thought that telehealth appointments, the patients would be incredibly patient. They would show up, they have their computer, they can write emails, they can surf the web. There's plenty of other options that they have at their disposal while they're sitting and waiting. In contrast, in person, they don't have the same thing, but we actually empirically found quite the opposite. So it turns out that in-person patients are more patient. They show up to the clinic and they're willing to wait for when and if the service will actually happen, whereas telehealth patients were more likely to leave without being seen if that provider was not readily available at the scheduled start time. Now, upon reflection, we thought, okay, well, actually, maybe this makes sense. And some of you are saying, well, I think that makes sense as well. You took the time to drive all the way to the clinic, pay for parking, blocked your entire day off for this. You are going to see your provider, right? It doesn't matter how long you need to wait. Whereas in the telehealth setting, you know, it's easy to just walk away from your computer and go do something else. There's a really limited setup cost. Additionally, depending on your telehealth environment, you're sitting in a virtual waiting room. So you might get a message that says your provider will be with you shortly, but you don't have a good sense of what shortly means. Whereas if you're sitting in a clinic and you see it's stuffed with patients who are all waiting, you know that the provider's running behind schedule. You get some sense of what your expected waiting time is likely to be. And so we wanted to understand a bit better kind of what are these two levers of information or costs, I guess, that could impact patient behavior. And again, motivated by this online environment, is there a way that we could use waiting time information, sharing the queue length? Now, many people in our field have spent a lot of time looking at that, but how does that compare to having somebody incur a sunk cost before they decide to enter the queue? And so that's really what we are trying to understand in this particular, right? So as I noted, there is a vast amount of literature. I would be, if I tried to summarize all of it, I would use up all of my time today just about providing waiting time information. A lot of it is obviously on the modeling side. There's also been empirical work trying to understand how this impacts customer behavior. There's also been quite a bit of work on sunk costs, primarily in the behavioral economics and psychology fields, to understand what is the impact of sunk costs. And so, you know, we have a lot of information about kind of from a modeling standpoint that, you know, rationally, we should ignore sunk cost. Humans should ignore sunk cost. We should only make decisions about what is going to happen in the future. But this has been shown not to be the case. Humans do not act rationally in many, many dimensions, but certainly not with sunk cost. There's actually empirically been shown that humans have a greater tendency to continue with an endeavor once they've made some investment. And this investment can be actual financial investments. It can be effort, exuding some effort, or just time that they put into that. And so the majority of research has shown that this sunk cost effect actually leads to worse outcomes. There'll be overinvestment by customers, overconsumption, because the rational person would decide to abandon and leave. Interestingly, there has been some recent work that actually shows that sunk costs could have benefits when we actually think about customer behaviors, and particularly for customers who have self-control issues. The sunk cost can actually help reduce people from overinvesting, over-consuming, and actually having the right behavior. So what we want to do in this work is look at recognition. Humans do not act fully rationally with respect to sunk costs. So can we use this as a lever for system design and trying to get good behavior amongst our customers? All right. So that's our goal for this work. Any questions so far?
Yes, Carrie.
Sure.
I have a question about the information asymmetry between telemedicine appointments and in-person appointments. So I could imagine that patients who are waiting in clinic, they could observe the queue lines, whereas for a telemedicine appointment, if they log in to the online portal, they may not see any information. So are you able to control for that in the study?
So in the empirical work, we don't have like great visibility itself into what's happening in the waiting room, in part because there's a mess of data and timestamps. We use a proxy for whether or not the physician is still with another patient. It's actually that challenging. But I think that that's exactly what we're going to try to model, is that what is the value of giving visibility or queue length information, and how does that compare to having customers incur a sunk cost? And when should you do both, none of them, or one and not the other? Because these are all levers that will impact the behavior of the customers.
Yeah, thank you.
Sure. Yeah, Shane.
Yeah, sorry, I was just curious. Please just say, I'm going to say it next if you're going to say it next. But I can see like one approach is to say sunk costs are a given and sunk cost behavior is a given. Now, what can we do within that context? And then the other thing you could do is you could say, well, now I want to sort of nudge the behavior and change the reaction to sunk costs. Which are you doing?
So we are going to, well, first I want to make sure that I'm going to show you that actually sunk cost does have an impact on the patients of customers. So I'll show you a quick experiment on that. But we're going to be modeling and saying that because there's this behavior, how do we actually tune the amount of sunk costs the customers incur in order to get the behavior we want? And in this case, we're trying to maximize throughput. And there's a lot of different behaviors you could try to do. It would be interesting to see if we can change the way customers respond to sunk costs, but I don't know how to do that. So I'm not going to try to, at least for now.
Thank you.
Sure. Other questions? Okay, so let me just first walk you through a quick experiment that actually highlights that sunk cost actually has an impact on service completions. And then if so, how do we tune it to maximize throughput. So our experiment is in a online environment. We're using Amazon Mechanical Turk. I want you to just forget the whole healthcare motivation now. We're looking in a general service setting. Amazon Turk has nothing to do with healthcare here. It's just an online environment. And there's 4 stages at what we are looking at. Essentially, there's an initial qualification task. And if the user is deemed qualified, they can go to the main task for a larger payment. So let me walk you through the 4 stages. So the first qualification task is we have a bunch of images. So you can see the bird here, and there's a drop-down menu. You need to identify what the image is. And for completing the qualification task, all users will get a base payment of 10 cents. Here, we're going to actually randomize people to either having a low sunk cost. They only have to answer 4 questions. This takes on average 30 seconds. Or a high sunk cost where they have to answer 30 of these questions, which takes about 3 minutes. So the sunk cost here is in terms of time and effort. Then we put the customers through a waiting period where we tell them that we are trying to verify their eligibility for the next task. Everybody is eligible for the next task, but they don't know this. So we're saying we're looking through their results. It's going to take some time. We don't tell them exactly how much it is. If they get frustrated, they can always quit during that waiting time. And they'll still get paid that base payment, but they don't get the opportunity to get the bonus payment of doing the main task. Every single person was made to wait exactly 6 minutes. What we then do is we actually require the customer to click, once they've been verified after those 6 minutes, they have 1 minute to proceed to the next task. So what we wanted to try to make sure is that we were getting some level of synchronous behavior where people didn't just wander away from their computer, come back an hour later and say, oh, great, I've been verified, I can proceed. So they needed to actually proceed within 60 seconds. So once they do that, don't laugh at the actual task. Jimmy selected it, although it's remarkable. This is actually a very challenging task, I would say. You have to identify whether the image is a muffin or a chihuahua. We don't actually care how well they do. But if they complete this, then they get $1. And so what we really wanted to understand, again, the actual task that we had them do had no bearing on the experiment, but we wanted to see what's the difference between those who were given a low sunk cost or a high sunk cost. And so what we found is we recruited a total of 425 participants. They were randomized, so we had 212 in the low sunk cost and 213 in the high sunk cost group. And these are their abandonment rates. And we found that the difference is statistically significant. So, I mean, what I want you to take away from this experiment is that indeed injecting the sunk cost decreases the likelihood of customers abandoning the system. And so recognizing now we have in 2 different environments, the telehealth environment and this mechanical Turk, that people respond to sunk costs, we want to model this and understand how we can use these levers to optimize our system. So there's again quite a large body of literature in our community about the queuing models that capture these factors. So ultimately, we are trying to model the behavior of customers. So it's related to the behavioral queuing literature. There has been some work on sunk costs in queuing systems. Most of those works actually assume that the customers are fully rational, whereas in contrast, we are explicitly capturing the fact that humans are not rational, and how can we leverage that to do system designed? And so that's obviously related to bounded rationality, and we're taking this behavioral perspective. All right, so I promised you I would get to a model. So here is my model. We have a two-stage model that is based on a standard MM1 queue, okay? So in the first stage, we have an exogenous arrival rate, lambda 0, and there's a decision by the customers when they come to the system. Should I enter the system? If I do, I have to pay a sunk cost S. And if I don't, if I leave the system, then I don't have to pay anything, but I also don't generate any utility, all right? In the second stage, so once people have made this decision, and I'm going to say Q1 are the proportion that decide to enter the system, I have another decision, and I have to decide whether I'm going to enter the queue and wait, or I can now leave the system. We assume that if someone decides to enter the queue, they're going to stay in the queue. So I'm looking primarily, I'm looking at balking in this model. We've normalized service rates to 1 for simplicity. Everything extends for an arbitrary arrival rate. And it's based, the decision here is going to be based on the information that's provided. So we as a system designer decide, do we provide queue length information or do we not provide queue length information? If someone decides to enter the queue, they incur a waiting cost that is proportional to how long they wait, so CW. Once they complete service, they get reward R. And the way that we're capturing the sunk cost aversion of the customer is through this cost minus theta S. So theta is a parameter that captures the sensitivity of a customer to the sunk cost. And so depending if your sunk cost is really large and your aversion is very large, then this cost of balking will be quite large. If there's no sunk cost, or if you're fully rational and theta equals 0, then you may not incur any cost with balking. All right. So this is our model. Any questions on the model before I go on?
Yes.
Yes.
So for the first stage decision, so is the decision instantaneous in the sense that customers, where does that Q1 come from?
Q1 is the proportion of customers that decide to enter the queue. And so they're going to be making this decision based on a queuing game and their understanding of kind of the equilibrium behavior of the system and what their expected utility will be if they enter the system or if they balk and just leave the system at that time.
I see. So their waiting time information is the expected steady state waiting time as a result of the whole game.
Exactly.
Okay.
So they're making this fantastic. So at this stage, they are making the decision based on their expected waiting time. In the second stage, they may or may not have information on the actual realized wait that they will have.
Okay, yeah, got it.
Because that's up to the service provider to decide whether or not to give that information.
Okay.
Is theta a constant or a customer specific value?
We're assuming that it is constant. So it's kind of the average behavior for all the customers. All right. Great. So I guess I mentioned this a bit. Customers are strategic. Their goal is to maximize their own utility. And so the service provider is trying to maximize throughput of the system given the customer's choices. So this is the system throughput. And there are 2 control levers for the system designer. So the first is whether or not to introduce a sunk cost, and if so, how large it should be. And then the second is what information, whether or not to reveal real-time queue length information. So if they decide to provide information, they will provide exactly upon entering the second stage, what is the current queue length. If it is an uninformed system, the customer gets no information about the queue length, okay? And so again, the customers are strategic. We enter into a queuing game, and the goal of the service provider is to maximize the equilibrium throughput subject to the customer's best response. Right. All right, so I'm going to start breaking down the analysis from the customer's standpoint, and then we'll bring it back together to, based on how customers behave, figure out what the service provider should do.
Okay. Question, Carri?
Yes, please.
Okay, so you say that customers are strategic. And yet I know that like the motivation was like we're trying to model the irrational behavior of customers. So is the idea we're going to model that irrationality by saying they are rational if we give them this extra sunk cost?
Exactly.
Okay, thank you.
So we assume that they are trying to maximize their own individual utility, but the irrationality comes in the fact that they have this aversion and this behavioral parameter. All right. So let's start with the uninformed customer's problem. And I'm going to work backwards. So I'm going to start from the second stage. I'm sure you all anticipated this already. So I want the customer is going to make this decision to maximize their utility, where they are making this decision. Should they join the system? So then that means they're going to incur their weight. Or do they balk? And this is where that behavioral parameter is going to come in, this aversion to balking due to the sunk cost. And here, this expected waiting time is an endogenous expected waiting time that depends on how the customers are going to actually respond. In the first stage, the customer is making the decision, should they join the queue or should they balk? If they balk, they incur no costs, but also don't make any, generate any utility. If they join, they have to pay that sunk cost. And then this is their expected utility given what's going to happen in the second stage. Now, this is interesting here how we're going to try to model this. We're actually going to assume that the customers believe themselves to be fully rational in the second stage. So you can look at the contrast between this expected utility and the actual, if you took expectation over what's happening in the second stage. Here, we don't have this cost of balking and that fallacy of the incurring that sunk cost. So you may be thinking, why on earth are we doing this if this is not what they're doing? So in 1999, there was a study by two individuals in the psychology literature and found that humans vastly overestimate how rational they are, despite the fact that they see other people being irrational. So they know that behavioral factors exist, that people are generally irrational, but they believe it for everybody else except for themselves. And so we wanted to model that within our system. It turns out it's not like a crucial assumption for our model. And if we incorporate this cost in here, the results qualitatively hold true, but obviously quantitatively it will have an impact. All right, so this is what's happening for the uninformed customers. And it turns out that we are able to characterize the equilibrium proportion of customers who join and wait in the first, oops, that should say second stage there. So you can see, so these are the proportions, and there's two different cases, but you can see in the second stage, everybody always waits. They always enter the queue. And this is not surprising because in the uninformed setting, once you get to the second stage, there's no new information that's provided to you, right? And so if you were fully rational, you would stay. And the existence of the sunk cost is only going to make you more likely to stay because you don't want to have to pay that sunk cost. So in the second stage, everybody stays. In the first stage, it depends on the arrival rate. If the arrival rate's really high, then people aren't going to want to end up waiting, and so they're going to balk. Otherwise, if the arrival rate's sufficiently low, everybody is going to join. So what this means is in the uninformed customer's case, that the sunk cost can only hurt the service provider. So it's the more sunk cost you incur that makes people, they don't want to have to wait in the second stage, but they also don't want to have to pay that sunk cost to join and wait in the first place. And so you can see in the first stage, what's happening on the x-axis is the sunk cost. On the y-axis is the proportion that are going to join. As you increase the sunk cost, fewer and fewer people are going to join the system. And so here, we're actually able to characterize the equilibrium throughput for the uninformed customer. All right. All right, let's go to the informed customer, which is a little bit more nuanced. So again, we're going to work our way backwards. We're going to start in the second stage and same decision. Should we wait or should we not? And so here the customer has, if they don't wait, if they balk, they're going to pay that sunk cost aversion cost, which is the minus theta times the sunk cost. And if they decide to wait, they're actually making this decision based on the actual realized number in system when they enter into the second stage. So they have exactly the queue length n. And so here you can show very straightforward that it's a threshold policy. They're going to join the queue if the number in system is below some threshold ns. Otherwise, they're going to balk. In the first stage, now we have that similar decision. Do they join the system or do they balk and make incur no cost, but have no positive revenue? And so if they join, they pay their sunk cost, and then they have their expected utility in the second stage. Here, again, we are going to assume that the customer believes themselves to be fully rational in the second stage. So this expected utility is over the queue length distribution up to a different threshold. They're actually going to, if you assume yourself to be fully rational, you'd actually balk at a lower threshold than if you had that sunk cost. The sunk cost makes you more willing to stay. And so these utilities, the expected utility, if you're fully rational, is not the actual expected utility that you're going to get with the actual threshold and that sunk cost that you're going to pay for leaving. All right. So here, we can again characterize the equilibrium strategy of the informed customers by the proportion of those, again, it should say second stage, those who join in the first stage and those who wait in the second stage. And so let me kind of parse this. In the first stage, they either all join or some fraction is going to join the system. And this fraction, so lambda f, is a parameter that essentially captures whether it's as you change the arrival rate to the exogenous arrival rate to the system. What is that arrival rate so that your actual utility of joining in the first stage is equal to 0? If the arrival rate is higher than that, then the utility is going to actually start to become negative. So we're actually able to show that it's monotonic. And so this is kind of the threshold at which this total number of customers are going to join the system. Anything above it will not, and below it, all will try to join to get up to that, because it's always a positive quantity. And so we can characterize this parameter as a solution to a fixed point equation. So what this means is in the first stage, either the arrival rate is sufficiently low that everybody joins, or it's high enough that people join just up to get exactly 0 utility. In the second stage, the proportion that decide to join the system, now they get real-time queue length information. And so it's determined by, this is essentially that proportion that's determined by how many are coming in from the first stage, and also the threshold for whether or not people decide to join the queue in the second stage. So if we put all of this together, and I'm just putting the equation here, but I'll try to show some pictures in a minute to give a little bit more intuition, is that we can characterize this equilibrium throughput if we assume that everybody is informed. And so you can see now how the arrival rate and the sunk cost are really impacting the throughput. So let me parse it into the different stages and how it comes together to give you a little bit more intuition about what's happening here. So this plot on the left is the proportion that join at the first stage, given the amount of sunk cost, right? And so this is similar to in the uninformed, it is non-increasing in sunk costs. Sunk cost is only going to have people be averse to joining in that first stage. And so there's some point where the sunk cost gets sufficiently high that it starts to discourage people from joining the system. The middle plot is the proportion that join in the second stage. Now they're being revealed information based on the sunk cost. And so there's a couple of observations that you may see. So first, you get these discontinuities. And this is because of that threshold, the decision to join at an individual threshold. And so depending on how you tune the sunk cost, it will make that threshold jump up or down. And so that's where we get the jumps in the proportion. The other thing you see is that in contrast to the first stage, in the second stage, the sunk cost is non-decreasing. The proportion that join is non-decreasing in the sunk cost. So these are moving in opposite directions, right? So in the first stage, the sunk cost is discouraging people to join. But once they've joined, that sunk cost keeps people in the system. And so what that tells you, these trade-offs kind of end up having this picture in the throughput that we can actually want to try to tune the sunk cost to maximize throughput in this particular setting. And you have to do it carefully. Otherwise, you could end up substantially impacting and degrading your potential throughput. All right. I want to put everything together now to think about that service provider's optimal policy now that we understand what's happening for both types of customers. And so here's the optimal policy to maximize throughput. So there's a threshold, there's a lot of thresholds in this particular model, don't worry about exact values, just know that we can actually characterize them. I want to give you more about the structure of what's actually happening with the policy. So here is an axis that is looking at that external exogenous arrival rate to the system in the first stage. And essentially it's split up into 3 regions. So if the arrival rate is sufficiently small, then you want to encourage people to join the system. So there should not be any sunk cost. And because the arrival rate is sufficiently small, essentially everyone's going to join because their expected utility is going to be quite high. And you don't want to provide them with queue length information. Because in expectation, they believe that their waiting time is going to be small. But if they get the bad realization where the queue length actually is large, they're going to leave the system. So the only thing the information is going to do is discourage people from joining. So in this low enough arrival rate, you should not have a sunk cost and you should not provide waiting time information. At the other extreme, when the arrival rate is really, really high, then you want to only provide waiting time information. You actually do not want to have a sunk cost because that sunk cost is going to discourage people from joining the system in the first stage. And the queue length information in the second stage is actually going to be sufficient to ensure that we're getting the right behavior of the customers. And so you only want to provide information on the waiting time. The sunk cost will actually hurt you. And the good news is that actually there is a region where you do want to have a sunk cost. Otherwise, we'd spend all this time analyzing a model for no reason. So there is a region where it's actually optimal to both have a non-zero sunk cost and provide waiting time information. And so this is where kind of that delicate balance of let's use the sunk cost to keep people in the second stage. And so that'll get them in. But we also have to provide enough waiting time information so that they can make the decision accurately. So that's kind of the main takeaways from our model. Let me give you a little bit of intuition of or kind of insight into what this all means with some numeric examples. So first in this figure, I'm trying to look at what is the optimal policy that we had just described there for different system parameters. So on the y-axis is the exogenous arrival rate to the system. On the x-axis is our behavioral parameter theta, which is kind of the captures how much of a sunk cost aversion there is. So consistent with our theoretical results, if the arrival rate is sufficiently small, no sunk cost, no waiting time information. If the arrival rate is large, you only provide waiting time information. But there's actually a very large region where you want to actually have a sunk cost. And you can look, I presume no one can actually see the numbers here because they're quite small, but the color map kind of highlights how different they are. And so it ranges from 0.5, and the actual values don't matter because of the parameters, all the way to 0.07 up here in the purple. So really all I want to show is that there's an order of magnitude difference in what the optimal sunk cost value should be, depending on these system parameters. And so we see that it actually matters a lot, but does it matter in terms of what the actual performance is of the system? So we wanted to understand what is the impact of introducing a sunk cost. And so here we're looking at this comparison between, I'm going to use the optimal policy of sunk cost and information or no information, and comparing to just optimizing over whether or not we provide waiting time information. So setting sunk cost equal to 0, and then you decide, the service provider decides whether or not to give queue length information. And so same kind of X and Y axis, the theta parameter on the aversion to sunk cost, external arrival rates. Now in these gray regions, there's no sunk cost. So obviously having a sunk, there's no benefit to having the optionality for a sunk cost. But in this region where you want to have both a sunk cost and provide waiting time information, there's a huge benefit in terms of system throughput of adding in the sunk cost and optimizing it. So if you can't see the actual numbers, it's up to 35% increase in throughput by appropriately tuning the sunk cost. So that hopefully convinces you that it's really important to actually design your system with the sunk cost in mind. But then you may be thinking, well, how on earth am I supposed, you say that it matters that I optimize my sunk cost, but it depends a lot on these system parameters. What if it's challenging to estimate those parameters? So what we wanted to do is look at a sensitivity analysis to that sunk cost. So this is a behavioral parameter, theta. Actually trying to estimate precisely could be very challenging in practice. Our experiment that I showed you at the beginning of the talk just shows that people have an aversion to sunk costs. But it's actually very difficult in that particular setting to estimate theta. We can't estimate theta from our experiment, in part because you need to have people learn kind of the queuing dynamics through repeated interactions. And in most settings, it's challenging to find participants to do that. So we wanted to understand what is the loss in throughput if that estimate of theta is incorrect. And so here we're saying that we're having an overestimate by 1%. So this is the worst case reduction. So I'm sampling over all possible misestimates of that theta parameter, optimizing under the incorrect theta, and then comparing the throughput evaluated at the correct theta of that misestimated system to the optimized system. And so here it's only a 1% overestimate. So it's very, very small, but the actual reduction in throughput can be huge, up to 25% reduction. So you need to estimate this parameter well. All's not lost. If you look in contrast, so this is overestimating. So thinking theta is bigger than it actually is. What if you think theta is smaller than it actually is? And so if we allow the same 1% deviation, there's actually no impact on throughput by having an underestimate by 1%. If we allow 5% deviation, there's a little bit of an impact. It's quite small. It's on the order of a couple of percent. And even up to 20% deviation of that estimated parameter, the reduction in throughput is about 5 to 15%. So there's this big asymmetry in the impact of misestimation. And so let me give you a little bit of an intuition of why that's happening. So let me bring you back to our figure that looked at the throughput as a function of sunk cost in the second stage when you have information. You're only going to have sunk cost when you also provide queue length information. So this all comes from these discontinuities due to those thresholds of joining or not joining. So if we look at where these discontinuities happen, it turns out that they are non-increasing in that theta parameter. So what ends up happening is that this throughput is going to jump at the sunk cost when you go from just to the left of the discontinuity and just to the right of it. If you underestimate the point at which this discontinuity occurs, which is happening, you'll underestimate that point when you when you overestimate theta, then you're going to be just to the left of the discontinuity. But if you actually underestimate it, you're going to be to the right of the discontinuity. And to being to the right of the discontinuity, I mean, in this particular case, it has no impact on the throughput for quite some time. Now, if you're to the right of it by a lot, of course, your throughput's going to go down, but there's a lot more leeway than when you have this cliff that happens when you have the overestimate. So kind of the conclusion there is that you want to make sure if you're going to be misestimating theta, you want to underestimate that. And I'm going to really make sure that this point gets drilled into your head to show you one more experiment and compare to what happens if we misestimate theta or if we ignore the sunk cost. So maybe if it's challenging to estimate theta, you should just not introduce a sunk cost in the first place. You should only optimize over whether or not you provide queue length information. And so on the left is if you are overestimating the theta parameter. On the right is if you're underestimating the theta parameter. And you can see the amount of leeway we give is quite different between the two of these. And so let me just interpret what's happening here. So in blue, the blue is saying that optimizing over the wrong estimate, the misestimated theta, is actually performing worse than ignoring the sunk cost. The red is saying it's performing better than ignoring the sunk cost. So we knew that underestimating by 20%, there was some reduction in throughput, but you still get up to 20 to 30% gains over not including a sunk cost at all. So this is quite substantial. But if you overestimate it, you might actually, in some instances, be better off ignoring the sunk cost, but not always. So you actually need to have a good understanding of how much noise there is in the estimates that you have provided. So let me just wrap up. We motivated this by some prior empirical work that we saw in observational setting. And then we further validated using a controlled experiment to show that a higher sunk cost leads to lower likelihood of abandonment. We wanted to incorporate that into a game theoretic queuing model and look at this contrast between having sunk costs and providing information, waiting time information. If you don't provide waiting information, you don't want to introduce a sunk cost. But if you do provide information, having a non-zero sunk cost can be really, really helpful. And all of this is to say, finally, humans are challenging creatures to fully understand. If we aren't able to pinpoint their sensitivity to the sunk cost, it's better to underestimate how they behave. So with that, thank you so much for all of your attention. Happy to answer any questions that you may have.
All right. Thank you, Carri, for a really interesting talk. So are there any questions?
Yeah, super fun, Carri. Thank you. I guess the sensitivity to theta is really striking, and that made me wonder about the sensitivity with respect to the form of the sunk cost in the second stage that you had. Can you say anything about that?
The short answer is no, because we haven't looked at others. My guess is because in the second stage, you essentially have this threshold policy. Even if you change that functional form of how it depends on S, you'll still get that threshold behavior. And so you'll still have this underestimate inclination. I'm sure the functional form, it'll depend highly, will impact like how sensitive it is, and maybe could mitigate some of that, how big that drop is at that threshold. But beyond that, I have no idea.
Thank you.
Sure.
And also for the sensitivity analysis with respect to theta, so if you underestimate theta, you also face the possibility of transitioning to a different parameter regime where the optimal policy changes. And so the estimation in the performance of throughput changes, so already takes that possibility into account.
Yes, exactly. So it captures the fact that you may end up not including a sunk cost at all, because theta has been so poorly estimated. But it's still, so that's, I mean, I think it's the intuition now, once you like look at the figure, it makes sense why it's so asymmetric, but it was a little bit shocking to us, and how big the difference could be in terms of throughput.
Could I ask another question about that? Like, so throughput is a great objective, I think, for some settings. And then I can imagine others where you have diabolical doctor who wants to maximize something else. I don't know what else, right? And they want to doctor the policy to ensure that they maximize some other performance measure. I guess if there's not enough learning in the customers, they'd get away with it.
So it's interesting. I love that you're saying they're diabolical. So I think throughput in one way is a measure of access, right? And so it's like, I want to treat as many patients as possible. Also, it's aligned with, I want to maximize my revenue if we are in a fee-for-service model. So I think there's some alignment, but you could think about using a sunk cost, and I need to spend some time thinking about this more carefully. Is like, it's a way to actually ensure access and a sufficiently low waiting time once people decide to enter the system. So I'm thinking out loud, but you can imagine there's a lot of these now concierge medicines where you can pay a fee and you're kind of guaranteed more access. You're guaranteed same day visits with your primary care physician. It's not the same dynamic because you only pay that sunk cost once. But it's an interesting lever that might be able to be used to try to get towards, I don't know, maximizing throughput subject to a waiting time constraint. And maybe it's easier to do that than just trying to use waiting time information to get the behavior you want.
Love it. Thank you.
Sure.
I was wondering about, so I know there's, okay, this might be about abandonment instead of balking, so maybe the dynamics get different. But I know there's this sort of classic result that last come first served is like revenue optimal in some sense. Like if basic has some having to do with externalities, right? In first come first served, if you join the queue, you're incurring an externality on everyone who will join after you if you decide to enter. Whereas in last come first served, when you sort of make the decision to leave, like you're always at the back of the queue. I'm definitely not doing a good job describing this. I think it's Hassan in the 80s in Econometrica. So I was wondering if you think that like many of the dynamics might be the same, sort of if you swap out the details of balking and first come first served for something like abandonment and last come first served, or would you expect something completely different? Yeah.
Yeah, that's a good question. So we, at least for the service settings that we were thinking, we thought that last come first serve would be hard pressed to justify. I think it's an interesting question. We need to look at it more carefully. My hope is that I've convinced at least some of you that this is an interesting lever, and so there's a lot more work that can be done to try to understand what the impact of the behavior would be. You know, it's interesting because so I think some of those results obviously in the absence of sunk cost, those hold. And so the sunk cost is going to just get people more likely to stay in that second stage. And so like maybe going back to Shane's point, like maybe we can actually achieve kind of similar behavior that we would get with the last come first serve. I'm just totally making this up. With the sunk cost that you're not able to do if you're not allowed to have a sunk cost. So there could be some weird interplays, but I'm pining and would need to sit down and try to work it out to see if any of these things might hold.
Right. And I guess, yeah, maybe a less wild idea than last come first served is more complicated information design. And
Sure.
which you could also, that question has probably been studied in first come first serve with information design versus last come first serve, but you can apply the same insights here.
Yes. And so it could even be like a different decision of like when do you actually provide queue length information rather than just a binary measure.
Thanks.
More work to do.
Yeah.
And if I'm thinking about so applying the insights to the healthcare application with in-person telemedicine visits. So I guess for that application, so first of all, patients' sunk costs in terms of travel time are not up to our control. And secondly, the in-person clinic, so patients may already have waiting time information by observing the queue length there. So then is the opportunity for that application in maybe charging different fees for patients choosing between person versus telemedicine visits to vary their sunk costs?
I mean, I guess I'm trying not necessarily thinking between like how do you, because in some ways the patient population could be different between a in-person and a telehealth setting. So their theta parameter actually might be different for the same individual, depending on whether it's a telehealth or an in-person visit. But I think to your point, in the telehealth setting, what we were thinking, there's a couple of ways to try to inject a sunk cost. One could be, you log on and you have to fill out all these forms, which many of us have to do. And so that's like a time and effort. It could be that you have to watch a education video about the benefits of hand washing or vaccination, or you have to pay your copay up front, or there's a cancellation fee, right? And then you could actually provide waiting time information rather than just saying your provider will be with you shortly. It's, there's the provider is with there's two patients in the waiting room ahead of you or whatever. And so trying to provide that type of information could be helpful.
All right. So I think with that, let's thank Carri one more time. Thanks again, Carri, for a great talk.
Thank you for having me. Take care.
Thank you, Carri.
Bye, everyone.